children. Welcome to today's episode on Stereoisomerism in Organic Compounds. ਅੱਜ ਅਸੀਂ organic compounds ਵਿੱਚ stereoisomerism ਬਾਰੇ ਗੱਲ ਕਰਾਂਗੇ. Unlike the atoms in constitutional or structural isomers, stereoisomers ਵਿੱਚ atoms same way connected ਹੁੰਦੇ ਹਨ. Stereoisomers differ only in the way the atoms of a molecule are arranged in space. Children, first of all, let's understand what stereoisomers are and which compounds exhibit stereoisomerism. Do you know the difference between constitutional or structural and stereoisomers? What does the name suggest to you? Yes, you are right. In constitutional isomers, difference lies in connectivity of atoms in a molecule, and in stereoisomers, difference is in spatial arrangement of atoms while connectivity of atoms is same. When different forms of a compound have the same structural formula but differ in relative arrangements of atoms or groups in space within the molecule, these are known as stereoisomers, and the phenomenon is known as stereoisomerism. Stereoisomerism is basically the feature of stereo centers which could be a multiple bond, cyclic structure about which rotation is restricted, or chirality center whose mirror image is non-superimposable. These are of two types: configurational isomerism and conformational isomerism. Let us first learn about configurational isomerism. Do you know what is the meaning of configuration? चलो मैं तुहानू दसदी हाँ. The fixed relative spatial arrangement of atoms in the molecule is known as configuration of molecule, and the isomerism arising due to different relative spatial arrangements of atoms is called configurational isomerism. Compound ਦੀ different forms ਨੂੰ different configurations ਕਿਹਾ ਜਾਂਦਾ ਹੈ. ਕੀ ਤੁਸੀਂ ਜਾਣਦੇ ਹੋ ਕਿ ਇਹ forms interconvertible ਨਹੀਂ ਹੁੰਦੀਆਂ ਅਤੇ ਇਹ isolated ਵੀ ਹੋ ਸਕਦੀਆਂ ਹਨ. ਉਦਾਹਰਣ ਲਈ alkenes ਵਿੱਚ different groups can be attached around the carbon-carbon double bond, which can be placed in two different arrangements. A attached groups molecule ਨੂੰ ਦੋ different configurations provide ਕਰਦੀਆਂ ਹਨ, ਜਿਨ੍ਹਾਂ ਦਾ molecular ਅਤੇ structural formula same ਹੁੰਦਾ ਹੈ. Screen ਤੇ ਇਹਨਾਂ ਨੂੰ ਵੇਖੋ. Here we find that A and B are two groups which are bonded to the carbon atom. They can either be placed on the same side or on the opposite sides as shown on the screen. Similarly, around a symmetric carbon or carbon attached to four different groups, two different configurations are possible due to different relative spatial arrangements of groups attached. As you see on the screen, in the given structure group, B is interchanged with group D about central asymmetric carbon. I am sure you all know that an asymmetric carbon atom is that to which four different groups are attached. With such swapping of atoms or groups about chiral center molecules acquire a new configuration, and the two forms obtained are configurational isomers. Please note that in such types of swapping, a different configuration is possible if there is odd number of swapping. With even swapping, configuration of molecule is retained. Different configurations वाले compounds ਦੇ physical and chemical characteristics भी एक दूजे तो different ਹੁੰਦੇ ਹਨ. So this was all about configurational isomerism. Atoms about which molecule can have different configurations are also called chirality centers or stereogenic centers or stereo centers. Configurational isomerism are further of two types which are shown on the screen: geometrical isomerism, optical isomerism. Let us first discuss about geometrical isomerism. These consist of configurational isomers in which relative arrangement of atoms or groups about a double bond or about the plane of cyclic molecule is different. It can be exhibited by compounds in which rotation about double bond or about the plane of cyclic molecule is restricted. Now let's see how it is exhibited in different compounds. Geometrical isomerism in alkenes. A given alkene can exist in two different configurations if its formula meets the requirements shown on the screen. For an alkene to exhibit geometrical isomerism, it should have any of the general formula as shown on the screen. Children, can you predict what is the cause of geometrical isomerism? As in pi bond, the two p orbitals that form pi bond have to be parallel to each other to achieve maximum overlap. Therefore, rotation about double bond does not occur. If rotation about a double bond did occur, then two p orbitals would cease to overlap and the pi bond would be destroyed. This hindered or the restricted rotation about double bond is responsible for geometrical isomerism in alkenes. Hence, alkene derivatives of the formula ABC double bond CAB can be written by two spatial arrangements as shown on the screen. In spatial arrangement 1, similar groups are present on the same side of double bond. This is called as cis isomer. While in 2, the similar groups are present on the opposite side of the double bond, so it is called as trans isomer. These spatial arrangements of groups attached can be expressed in two different ways as cis and trans form, E and Z form. Here, spatial arrangement 1 is called cis, whereas 2 as the trans isomer. Such type of geometrical isomerism is also called as cis-trans isomerism.
Let us now discuss few examples showing geometrical isomerism which are shown on the screen. The first example is of 2-butene which can exist as cis-2-butene and trans-2-butene. The next example is of 3-hexene which can exist as cis-3-hexene and trans-3-hexene. Similarly, let us have a look at one more example of maleic and fumaric acid. In this, maleic acid is in cis form, whereas fumaric acid is trans form of but2-ene-1,4-dioic acid.
Children, let us now learn about E and Z isomers of alkenes. If in an alkene, all the atoms or the groups attached around double bond are different, then their configurations are assigned in the form of E and Z. The E and Z configuration depend upon preference or priority of the atom or group attached around double bond. If high priority atoms or groups are on the same side of the double bond, then the configuration is Z, and if these are across the double bond, the configuration is E. Have a look at these on the screen. Now let us see how priority of groups attached is decided. For assigning the priority of the groups attached, few rules are followed. Let us have a look at these rules one by one. Rules for assigning priority. Rule 1. The relative priority depends upon atomic number of the atoms bonded to double bond of alkene. Higher the atomic number, more will be the priority of the group attached. Rule 2. If the two substituents on an sp2 carbon have same atomic number, then the atomic number of the next atom attached to the tied atoms is to be considered for priority. Rule 3. If an atom is doubly bonded to the another atom, the priority system treats it as if it were singly bonded to two of those atoms. Similarly, if atom is triply bonded to another atom, then the priority system treats it as if it were singly bonded to three of those atoms. Rule 4. In case of isotopes of an element attached to sp2 carbon, then mass number of atoms is to be used to assign priority to the group attached. चलो as the better understanding ਲਈ ਇਸ ਦੇ ਸਟਰਕਚਰ ਨੂੰ ਵੇਖਦੇ ਹਾਂ। ਇੱਥੇ ਇੱਕ ਰੂਲ ਦੇ ਮੁਤਾਬਿਕ ਆਇਓਡੀਨ ਅਤੇ ਬ੍ਰੋਮੀਨ ਹਾਇਰ ਪ੍ਰਾਇੋਰਿਟੀ ਤੇ ਹੋਣਗੇ। As the groups having high priority are across the double bond, so the compound will be assigned configuration E. ਹੁਣ ਸੈਕੰਡ ਕੇਸ ਲੈਂਦੇ ਹਾਂ। ਆਇਓਡੀਨ ਅਤੇ ਬ੍ਰੋਮੀਨ ਸੇਮ ਸਾਈਟ ਤੇ ਹਨ ਅਤੇ higher priority ਦੇ groups ਹਨ। Since higher priority atoms or groups are on the same side of the double bond, so the configuration assigned is Z, as shown on the screen. Let us now learn about geometrical isomerism in cumulative alkenes, that is, such compounds in which double bonds are adjacently placed. These compounds can be planar as well as non-planar depending upon the number of double bonds present in a molecule. Geometrical isomerism is exhibited by only those polyenes which are planar in nature. Planar polyenes. For a cumulative polyene to be planar, the number of double bonds have to be odd. Therefore, for these cumulative polyenes to exhibit geometrical isomerism, the number of double bonds has to be in odd numbers. Let's have a look at these on the screen. The first structure shows that there are even number of double bonds and is therefore non-planar. The second structure shows that there are odd number of double bonds and is therefore planar. You can very well understand which molecule is cis and which one is trans and why, as we have discussed it in a little while ago.
Children, let us now learn about geometrical isomerism in cycloalkanes. In cyclic compounds, there can be no free rotation about carbon-carbon single bonds because rotation would break the bonds and break the ring system. For example, 1,2-dimethyl cyclopropane exists in two isomeric forms as shown on the screen. These are cis and trans forms. Similarly, 1,2-dichlorocyclobutane can also exist in two different forms. Let us now discuss about geometrical isomerism in the compounds containing C double bond N. Oximes of aldehydes and unsymmetrical ketones, that is, aldoximes and unsymmetrical ketoximes, can also exist in two different configurations due to hindered rotation about carbon-nitrogen double bond. Due to this hindered rotation, these molecules exist in two different configurations as syn form and anti form. For example, benzaldoxime, that is C6H5 CH double bond NOH, has two different configurations which we are seeing on the screen. Children, geometrical isomerism in the compounds containing N double bond N. The simplest example in such compounds is that of azobenzene. In this molecule also there is a hindered rotation about double bond and the molecule can exist in two different configurations. The two different configurations are as shown on the screen, the syn form and the anti form. Geometrical isomerism in cyclo-alkenes. In such molecules, about double bond molecule can have two different configurations depending upon the ring size. Cyclic molecules in which the number of carbon atoms are 7 or less, only cis configuration is possible about double bond. Both cis and trans configurations are possible about double bond if ring contains 8 or more number of carbon atoms. For example, cyclo-octene exists in two different forms. Observe the structures on the screen. It exists as cis form and trans form. Similarly, in cyclodecene, two different forms are possible.
Let us now learn about the second type of configurational isomerism, that is optical isomerism. It is the phenomenon of having same molecular and structural formula of compound but having different effect on plane polarized light. Such compounds with same molecular and structural formula but having different effect on plane polarized light are called optical isomers. Let us now learn about plane polarized light. ਕੀ ਤੁਸੀਂ ਦੱਸ ਸਕਦੇ ਹੋ ਕਿ plane polarized light ਦਾ ਕੀ ਭਾਵ ਹੈ? Ordinary light is a beam consisting of electric and magnetic field oscillating in two mutually perpendicular planes. In unpolarized light, these oscillations are in all possible planes perpendicular to direction of propagation. ਜਦੋਂ ਇਹ light polarizer ਵਿੱਚੋਂ ਲੰਘਦੀ ਹੈ ਤਾਂ it interacts with it in such a way that light coming out of it has oscillations only in one plane and is called plane polarized light as shown on the screen. Let us now discuss about the optically active compounds. These are the compounds which are capable of rotating the plane of plane polarized light. These are of two types, dextro-rotatory. These are the compounds which rotate plane polarized light towards right direction or in clockwise direction. Levo-rotatory. These are the compounds which rotate plane polarized light towards left direction or in anti-clockwise direction. Criteria for optical activity. The absolute criteria for any compound to be optically active is dissymmetry. That is, it should not have any element of symmetry. Let us discuss about elements of symmetry. A given compound is symmetrical if it has any of the following: a plane of symmetry and or center of symmetry and or n-fold alternating axis of symmetry. Let us first learn about the plane of symmetry. ਜੇਕਰ ਕਿਸੇ ਆਬਜੈਕਟ ਨੂੰ exactly two equal halves ਵਿੱਚ ਇਸ ਤਰ੍ਹਾਂ ਕੱਟਿਆ ਜਾਵੇ ਕਿ ਇੱਕ ਹਾਫ ਦੂਜੇ ਹਾਫ ਦੀ ਮਿਰਰ ਇਮੇਜ ਬਣ ਜਾਏ ਤਾਂ it has a plane of symmetry. For example, ਸਕਰੀਨ ਤੇ ਵਿਖਾਏ ਜਾ ਰਹੇ ਕੰਪਾਊਂਡ ਵਿੱਚ plane of symmetry ਹੈ ਕਿਉਂਕਿ ਇਸ ਨੂੰ ਸੈਂਟਰ ਵਿੱਚੋਂ ਦੋ ਇਕੁਅਲ ਹਾਫਸ ਵਿੱਚ ਡਿਵਾਈਡ ਕੀਤਾ ਹੋਇਆ ਹੈ। ਜਿਵੇਂ ਕਿ ਤੁਸੀਂ ਸਕਰੀਨ ਤੇ ਵੇਖ ਰਹੇ ਹੋ 1 and 2 ਮਿਰਰ ਇਮੇजेस ਹਨ। ਇਸ ਲਈ ਇਸ ਮੋਲੀਕਿਊਲ ਵਿੱਚ plane of symmetry present ਹੈ। In the form shown on the screen, two parts from the center are not mirror images and it lacks in plane of symmetry. 1 and 2 are not mirror images. Hence, plane of symmetry is absent in the molecule. Let us now try to define center of symmetry. It is a point inside a molecule from which, on traveling equal distance in opposite direction, same type of atoms or groups are encountered. A center of symmetry is usually present only in an even numbered ring. For example, trans 2 4-dimethyl cyclobutane trans 1 3-dicarboxylic acid has a center of symmetry as shown on the screen. Dissymmetrical compounds are also called chiral and their mirror image is non-superimposable. If all the 4 bonds of carbon are with 4 different atoms or groups, it is called chiral carbon or asymmetric carbon. Chiral carbon is designated by an asterisk. Let us now learn about optical activity in compounds with one chiral center. Such compounds are optically active in nature as their mirror images are non-superimposable and are 2 different forms of a same compound with different configurations. These rotate the plane polarized light by same magnitude but in opposite direction. These are also called enantiomers or enantiomorphs. For example, bromochloroiodomethane exists in 2 different forms which are non-superimposable mirror images of each other. Let us have a look at the Fisher projections of the 2 isomers on the screen. All the physical and chemical properties of enantiomers are same except 2. They rotate plane polarized light to the same extent but in opposite direction. One which rotates plane polarized light in clockwise direction is called dextrorotatory and is designated by D or plus sign. One which rotates plane polarized light in anti-clockwise direction is called levorotatory and designated by L or negative sign. They react with optically active compounds with different rates. Optical activity in compounds with multiple chiral centers. ਜੇ ਇੱਕ organic molecule ਵਿੱਚ ਇੱਕ chiral carbon ਹੋਵੇ ਤਾਂ molecule chiral ਵੀ ਹੋ ਸਕਦਾ ਹੈ ਅਤੇ ਅchiral ਵੀ, depending whether it has an element of symmetry or not. For example, in tartaric acid, there are 2 chiral carbons and the molecule is symmetrical. It can exist in 3 different forms as we will learn just now.
Stereoisomerism in tartaric acid. Compounds which contain 2 asymmetric carbon atoms and are of the type C-ABC-C-ABC exist in only 3 isomeric forms. 2 of these are non-superimposable mirror images of each other and are optically active, and the third, a diastereomer of the first 2, contains a plane of symmetry, is superimposable on its mirror image and is not optically active. The inactive diastereomer is usually described as a mesoform.
Let us now discuss about the mesoforms or mesocompounds. These are the optically inactive forms of compounds containing chiral centers. These have a plane of symmetry and about this plane the 2 parts of compound rotate plane polarized light by same magnitude but in opposite direction. The net effect on plane polarized light is 0. This nullification of effect on plane polarized light within the molecule is also called internal compensation. The properties of mesoforms are different from those of the isomeric mirror image pairs. For example, mesotartaric acid melts at a lower temperature of 140 degrees Celsius than the D and L isomers at 170 degrees Celsius and is less dense, less soluble in water and a weaker acid. Let us now learn about diastereomers. These are two forms of a same molecule with same molecular and structure formula but are not mirror images of each other. For example, the mesoform of tartaric acid is a diastereomer of both D and L forms of acid. Similarly, the two geometrical isomeric forms of alkenes are diastereomers. Optical isomerism in unsymmetrical compounds with two chiral centers. Such compounds occur in four optically active forms or in two different enantiomeric pairs. For example, 2,3-dibromopentane can exist in four different isomeric forms as shown on the screen. In general, a compound possessing n distinct asymmetric carbon atoms exists in two n optically active forms. 1, 2 and 3, 4 are enantiomeric pairs.
Calculation of number of optical isomers. Organic compound, the optical isomers, the number is the structure ਅਤੇ number of asymmetric carbon atoms ਤੇ depends ਕਰਦਾ ਹੈ. The number of optical isomers may be determined from the knowledge of the structure of the compound as shown on screen. Case 1, when the molecule is unsymmetrical, number of optically active isomers A is equal to 2 to the power n. N is number of asymmetric carbon atoms. Number of mesoforms, that is M, is equal to 0. Number of racemic mixtures, that is R, is equal to A upon 2. Therefore, total number of optically active isomers is equal to sum of A plus M, which is equal to 2 to the power n. Case 2. When the molecule is symmetrical and has even number of asymmetric carbon atoms. Number of optically active isomers A is equal to 2 to the power n minus 1. Number of mesoforms M is equal to 2 to the power n upon 2 minus 1. Number of racemic mixtures R is equal to A upon 2. Therefore, total number of optically active isomers is equal to A plus M. Case 3. When the molecule is symmetrical and has an odd number of asymmetrical carbon atoms. Number of optically active isomers A is equal to 2 to the power n minus 1 minus 2 to the power n upon 2 minus 1 upon 2. Number of mesoforms M is equal to 2 to the power n upon 2 minus 1 upon 2. Therefore, total number of optically active isomers is equal to sum of A plus M, which is equal to 2 to the power n minus 1.
Let us now learn about racemic mixture. It is an equimolar mixture of D and L enantiomers of any optically active compound. It is optically inactive as the effect on plane polarized light due to D isomers is nullified by an equal number of L isomers present in the mixture. This nullification of the effect on plane polarized light is also called external compensation.
So children, ਹੁਣ ਅਸੀਂ ਅੱਜ ਦੇ ਟੌਪਿਕ ਸਟੀਰੀਓਆਈਸੋਮਰਸ ਦੇ ਅੰਤ ਤੇ ਪੁੱਜ ਗਏ ਹਾਂ। ਸਟੀਰੀਓਆਈਸੋਮਰਸ ਨੂੰ ਕਨਫਿਗਰੇਸ਼ਨਲ ਅਤੇ ਕਨਫਰਮੇਸ਼ਨਲ ਆਈਸੋਮਰਸ ਵਿੱਚ ਡਿਵਾਈਡ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ। ਕਨਫਿਗਰੇਸ਼ਨਲ ਆਈਸੋਮਰਸ ਨੂੰ ਅੱਗੇ ਹੋਰ ਜਿਓਮੈਟ੍ਰੀਕਲ ਐਂਡ ਆਪਟੀਕਲ ਆਈਸੋਮਰਸ ਵਿੱਚ ਡਿਵਾਈਡ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ। We learned that geometrical isomers can be divided into cis and trans and E and Z. Optical isomers can further be divided into dextro and levorotatory isomers. In our next session, we will learn about conformational isomers.
So I hope that you all have enjoyed today's lesson. Thank you students for the attention you have paid in understanding these concepts. See you next time. Till then, goodbye.